Hey there. So math is often a stumbling block for people who are interested in folding origami tessellations. And I think that the math for tessellations isn't actually that bad. It's just a little bit of a black box. So I'm here to explain what math actually is involved in origami tessellations and how to do it. So let's start with some vocabulary. There's some basic vocabulary words that we need to know to follow instructions for origami tessellations, and these include basic shapes. So you've got hexagon, square, triangle, and getting into less familiar shapes like rhombus, we might say equilateral triangle or right triangle, and seeing trapezoids as well. Seeing all of these different shapes and being able to visualize them in your mind's eye is very important for tessellations. Oh, and by the way, I'm working down my notes here, so you might see me glancing to the side. So then there's a couple more math words that we need to know for tessellations, especially twist-based tessellations like I fold, which are grid, line, and intersection. So when we have a grid, like the background of this paper is a grid, I'm going to be talking about, let's say, a particular grid intersection, so a place where lines come together. I might also talk about a grid square, and I might talk about a grid line, and all of these different things are ways to reference positions on a grid. So when we have triangle grids, we have very similar things. We have a grid intersection, but there's three directions that are coming together. We have grid triangles, and we have grid lines as well. So next up, we have counting and being able to add and subtract spaces as needed. And so we'll be able to say, okay, starting from this position on a grid line, we're going to count 1, 2, 3, 4 spaces out to the next target grid intersection. And so I'll often be saying things like that. Often it's like, okay, we're going to go 2 spaces from the valley, which I mark as a dashed line, to the next valley, and then the mountain will be on the far side of that. I'll often use colored pens to mark those. So I'll do my valleys in blue and my mountains in red, because rivers run in valleys and are blue. So there's a very good explanation for why I have my valleys blue. And then there's other words that are folding specific, origami specific. So you have valley and mountain, as we were talking about, and these are different directions of fold. And then you have, okay, we've got a valley next to a mountain. They're parallel to each other, and they're a certain distance apart, and that's called a pleat. So we've got valley, we've got mountain, and then the two together make a pleat. Then we can have interactions of these valleys and mountains. I'll draw a closed square twist here, and we've got kind of phantom mountains coming into the center. And we can have this be right-handed, because if I have my thumb up in the middle, my fingers along the mountain curl, I hit the valley of the same pleat. That would be a right-handed closed square twist. So there's these terms that start coming up where we have right-handed, left-handed, closed, open, and then square and twist. that are necessary to understand to follow instructions for tessellations. And then we get into, okay, what do we need for the actual folding process? So for the actual folding process, we're going to need a bit of multiplication. You could also think of it as division, depending on which way you go. So let's say I want to fold a 32-fold grid. Well, that is twice as many divisions as a 16-fold grid, which is an 8 times 2 times 2. And I'll shortcut to the end. This is 2 times 2 times 2 times 2 times 2. And so whenever I have a finished target number, what I need to do to find what I need to fold is the prime factorization. So let's do this with another number, let's say 24. If I have a 24-fold grid that I'm aiming for, then that's going to be 8 times 3, or 2 times 2 times 2 times 3. And so I have this odd division. So that's another layer. We've got even numbers and odd numbers. And the even numbers can be multiples of 2, they can be other numbers. So some special numbers that we see a lot in gridding are things that we can do just with divisions of 2. These are the powers of 2. So we've got 4, 8, 16, 32, 64, 128, and most people when they're beginning don't go past 32. This is kind of a good level, especially in the beginning. You don't want to invest in very large paper and very large workspace. You're going to be mostly working with 16 and 32-fold grids. The 24 is a nice middle number between 16 and 32. And several of my students have commented that they feel most comfortable folding on a 24-fold grid, especially in the beginning. So this 3, how do you get even divisions of 3 starting from a square? Well, what you can do is start with a square, and I'm going to mark halfway across this square. Now you might have noticed that this square outlines a 6x6 grid. And I'm going to do a quick demonstration of how you can get to that with folding. So if I've marked halfway across one edge, then I have some distance here that is half the distance on the bottom. So effectively, if we take the smaller distance to be 1, then the larger distance is 2. And if we fold diagonals, I'm going to rustle up a straight edge to make this a clean drawing. If we fold diagonals, on the boundaries of these two distances. So I've got my left edge of the top distance to the right edge of my bottom distance, the right edge of my top distance to the left edge of my bottom distance. These cross at exactly 2/3 of the way up. And this is mathematically provable, and I did prove it, but you don't need to prove it for yourself to use it to fold tessellations. And this works with any set of distances. So here we've got 1 above and 2 below, and these are different distances than the 1 and 2 that were used to generate them, but they are consistent. So we can do this with other distances as well. We could say, okay, I'm going to go for a division of 7. And so my bottom and the exact square that I have here is not as important for this, but I'm going to mark half on the top and then half again. It's going to be about here. And then I can have 3 on the top, 4 on the bottom. And when I draw my 2 diagonals, they're going to cross exactly on a grid intersection of this 7 by 7 square. Now I'll have a video showing more about this particular technique later on, probably in February. And we'll be seeing like more variations on this, how you do it on a rotated grid, etc., etc. But the important thing to know is this pattern holds true no matter what, as long, and it works for both directions, kind of mind-blowing that it works for both directions, as long as one more property that I hadn't mentioned, this edge that connects 2 of these distances is on a grid line already. So effectively, if we're starting with a square sheet of paper and we're doing a grid the standard way where the grid is aligned with the edges of the paper, then the edges of the paper are already grid lines, and we can use this technique as long as our 2 distances are touching both either the left side or the right side of our square. So that's odd divisions, and it's really addition. So 1 plus 2 equals 3. We just need to find, okay, where can we have a distance that's half as wide as the bottom edge? And then 3 plus 4 equals 7. Where can we have a distance that's 3 relative to the bottom edge is 4? And you start to get these patterns that show up where it's like, okay, say your target number of divisions is 5. Use one we haven't done yet. And so I can look at my list of multiples of 2, and I'm going to go ahead and put 2 at the top and say, what on this list is the biggest number that's less than 5? So 4. And I'm going to say 5 equals 4 plus 1. And then I'll say, okay, then I can have a distance of 1 at the top and a distance of 4 at the bottom. And that's how I'm going to get my target of 5 when these 2 cross. So that's odd divisions in a nutshell. And you might have noticed, hey, these don't have to be exactly aligned on top of each other. If we do this on a triangle grid, well, it works the same way. If we have a triangle grid, like let's say we've got this shape of triangle grid, and we want to do a division, and so then this distance is 1, this distance is 2, and we're gonna draw the diagonals and get that 2 to 1 ratio. Okay, so that's how you set up the odd divisions, but how do you actually fold them? So once you have the intersection, one side is going to be odd and the other side is going to be even. This is necessary because the only way that you get two numbers to add together, so adding two numbers together to make an odd number, is if one of them's odd and the other is even. There's no way around this. So odd number plus odd number makes even number plus even number makes even number, only odd plus even makes odd. So there's another little bit of math that is just there helping us out. And so we take the even side and we divide it in half. And so once we've taken the even side and divided it in half, then either this bit in the bottom is going to be even, or this bit in the top is going to be even. Because either we have an even number that's 2 times an odd number, or an even number that's 2 times an even number. Those are the only two options. And so if we divide it in 2, like let's say with this 7 here, we divide the 4 in 2 to get 2, and then we have a marker at our point, so we've got another 2, and then we have 3 up here. Then we can divide each of these 2's in half, and yes, that does mean picking up this initial fold and bringing it to our point. Luckily, with a square, we're constrained with exactly what we can do because we have these edges that we need to match up. And so we have more references than just line to point, which we can fold in an infinite number of ways. But if we do line to point and match up the edges, then that's actually like line to 3 points, which is basically line to line. But anyways, for today's purposes, we've got 1, 1, 1, and then we have 3 plus 1 is 4. So eventually, if you keep dividing things in half, you're going to get to an odd number. And if that number that you divided in half initially was a power of 2, one of these, then that odd number is going to be 1. And so then we have an odd number above plus an odd number below makes an even number. And we can divide that in half. So then we've got 2 and 2. And then we can divide those in half. And it all just cascades. And so we're aiming for an odd number. So we have a sum of an even and an odd number. And then when we put in our intersection, then we have an even side and an odd side. We divide the even side in half until it becomes odd, until we've divided it enough that it's odd. Then that odd number just under the intersection of diagonals and the odd number above it combine to make an even number. And we're set to keep on going. So when you're folding with odd divisions, it really is a matter of addition and recognizing odd and even and dividing even numbers in half. So that's pretty straightforward as far as math goes. Then after that, so that basically covers gridding, with one exception. So for beginner level, this is really all the math that you need for your grids. But once you go a little bit beyond beginner level, once you start customizing each grid for the different tessellations, then you start getting into rotated grids. And that sounds a little scary. It sounds like I'm going to start talking about degrees and trigonometry and stuff. But no. I mean, I used degrees and trigonometry to figure out the formulas, but once you have the formulas, then it comes down to, okay, on a square grid, we're going to take x minus y over 2x. And yes, these are variables, but we get them by counting along grid spacings, counting along grid lines. So let's say that I have this closed square and its neighbor is another closed square, but on the back. And we're going to have our mountain folds here. And you can see that if we keep on repeating this, the centers of these squares are going to keep shifting up and up and up. So what this x and y is talking about is, okay, from the center of this square to the center of that square, I'm going to go 1, 2, 3, 4, 5 spaces over and 1 space up. So then in this case, if x is 5 and y is 1, then this fraction, which I call a over L, is going to be 5 minus 1 over 10, which is, or I can keep that as 2 times 5 because we're going to factor that out anyways. So 5 minus 1 is 4. 4 divided by 2 is 2, and we get 2/5 as our fraction up the right-hand edge of the paper that we're going to put our mark to do our rotated grid. But that's a topic for a whole other video, and I do have rotated grid videos already, so head to my channel, check those out. And then we can do a very similar thing on triangle grid. On triangle grid, the formula is even easier. A over L for a triangle grid on a hexagon is y over x plus y. That's it. And so both of these were working along grid lines to find, like, okay, is this aligned with the boundaries of the hexagon? Is it not aligned? How can we make our central things align with the edges? And there's complications with like tiling breaks, etc., that we can get into, but that's kind of the more advanced side. For actually folding your first tessellation, forget this. Forget the odd divisions. Just do an even grid. And then once you have your grid, you start folding, you start using the hexagon, the triangle, the square, all of these different twists. Then you start saying, okay, how do I repeat this? And this is where we start seeing some vocabulary words that are less familiar, like rotational symmetry and mirror symmetry and translational symmetry. So let me write those down. We've got rotation, translation, and mirror. And so rotation happens around a point. So rotation is around a point, and it comes in types. So what we deal with grid-based origami tessellations are 6-fold, 4-fold, 3-fold, and 2-fold rotations. And when I'm saying 6-fold, I'm not talking about folds in the paper. This is a kind of a math lingo type thing where if you look on the Wikipedia page for rotational symmetry, they'll say, oh, sixfold rotation. So that's just a piece of vocabulary. And what we have here is these symmetries define shapes and how they connect together. So if I've got a collection of hexagons here, and let's pretend that this collection of hexagons keeps going forever, then I've got a sixfold point in the center of each hexagon, a threefold point where three hexagons come together, and a twofold point between pairs of hexagons. So this is characteristic of the hexagon symmetry. And I have videos on each of the six symmetry types that I'm going to talk about. When we get to fourfold rotational symmetry, that's the symmetry that's in a square grid or a square tiling, where we've got a fourfold position in each of our squares, and we have another fourfold position in the corners of the squares as well. So you see there's two different kinds of fourfold positions. And then just like the hexagons, there's twofold positions between each pair of squares. And that's the square symmetry. If we take this and we stretch it out and make rectangles, then we get the rectangle symmetry, which is 2 in each center, 2 in each intersection, and 2 in the long edges, and 2 in the short edges. So that's 4 different 2s. Center, intersection, long edge, and short edge. Okay, well what happens if we take that and we slant it? So there we've got rectangle. What if we say, okay, it's slanted over, do we still have the same kinds of symmetry? And actually, yes, we do. We still have 2 in the center, 2 in the intersections. And in this particular drawing, I don't have short edges and long edges. We'll go with the horizontal edges and the slanted edges. So this is what I call the parallelogram symmetry. So these are all very, very similar. And we can see a little bit of mirror symmetry in these types as well. Rectangle and square symmetries lend themselves to mirror symmetries. And one other type as well, if we have equilateral triangles, and I'll use what grid lines I can for this approximation here. Always fun. So with the equilateral triangles, you might be really tempted to say, oh, there's a 6 right there. It looks like 6. But what actually is going on here is that we have 2 different kinds of triangles. And so it looks like 6, but it's actually 3. So we've got the 3 at the intersections, the 3 in the dark centers, and the 3 in the light triangle centers. So that's 3 different 3s. With the square, we had 2 different 4s and a 2. Rectangle, we had 4 different 2s. Parallelogram, we had 4 different 2s. Triangle, we have 3 different 3s. And then there's one more symmetry type, which is columnar. And so I'm going to show it as these vertical lines, and they don't really end. We could have 2s along these columns. We could have mirror symmetries, and that mirror symmetry is like right hand to left hand, mirroring over. We can have a mirror between, like on a line between triangles. We can have it on a line between rectangles. We can have it on a line between squares. We can't have it for parallelograms because this parallelogram, if it was mirrored over the horizontal line, would end up down here. And that does not match with the parallelogram in place. Likewise, we can't have a mirror symmetry line in the hexagon symmetry because none of these lines go all the way through. They have to pass through a hexagon to continue extending. Each line is a very short segment. So mirrors are only possible on square, rectangle, triangle, and columnar or linear symmetries. And one thing I haven't mentioned yet is translation. And that just means moving something from one place to another. So if I have translation, that usually shows up in the columnar symmetry, where I'm taking something from one place, and usually this is if I don't have the rotational or the mirror symmetries, I'll often have something from one place, and then it shifts over to another, and there's no rotation, no mirror, just moving a little bit along the line. So that's really the math that you need for tessellations. It might be a little harder to see, like, okay, what thing on the paper is in what symmetry position. But with the hexagon, square, triangle, rectangle, parallelogram, columnar ideas in your head, you can start looking and see, oh, do I see a 6-fold rotational symmetry? Which is usually, do I see a hexagon twist? And say, bingo, that's going to be in the hexagon symmetry, and therefore I need to find out where are my positions of 2-fold and 3-fold rotational symmetry. Now, not every symmetry is going to be sitting inside of a twist. They often are, but sometimes not. And so I can have choices when I'm designing about, like, okay, if I have this start, am I going to continue that way? Am I going to put the symmetries further out? Am I going to do something different with it? So we've covered the vocabulary of tessellations, of the shapes and of the grid, and of the folding. We've covered counting and addition. And when we are putting things in, we want to make sure that we're putting them in the right locations. So we talked about grid intersections, grid squares, how to count along a line in a grid. And we talked a little bit about odd divisions, multiplication, prime factorization, odd divisions on both square and triangle grids. We touched a little bit on rotated grids, but that would take me another hour or two to explain. So there's another video already on my channel for that. We talked about like fractions and how we can use like dividing even numbers in two until they are odd numbers, and then take an odd number and a neighboring odd number, combine them together to make an even number, and then divide that by 2 until you have an odd number, and just keep on going. It's an iterative process, the gridding. And so we've got that side of things. We talked about the symmetries, where we can say, okay, let's try and find what the symmetric positions are. One thing I didn't mention yet is that with these hexagon symmetries, the twofold position is always and necessarily exactly between two threefold positions. This is just a property of hexagons, and it holds true on crease patterns, it holds true in the final folded form. Likewise, with these square symmetries, we've got our two different positions of fourfold rotational symmetry, and if you draw a line from one fourfold position through a twofold to the other fourfold position, that is going to make a right angle. Always. And this is something that I actually use in designing, where I have two different clusters that are around fourfold positions, and then I can draw a line and see where it makes a right angle to see where the center of my twofold position needs to be, and that tells me what twist to put there so that the pleats line up and the center's in the right place. And then we've got our mirror lines, our rotational symmetry, we've got our 6 symmetry styles, and we can get into more math related to tessellations, but this is really all the math that you need to fold them. We can get into math for designing. Some of it I've been developing over the last couple years. And even that is using these symmetries, using, oddly enough, a number line. You can connect twists together in an order, and then you can have distances between twists in that order. And that tells you things about designing. It's mind-blowing. And then we have like arrangements of twists. So if you've never seen a certain arrangement before, what you really want to be looking for in the crease pattern is what twists there are, how far apart they are, which ones lead to which other ones, and where are the positions of symmetry. So that last part, where are the positions of symmetry, is where it really comes in handy to know what symmetry options there are, because that makes it a lot easier to see. So if I grab some examples from over here of different ways of arranging twists, I'm just going to grab some stuff from Advent of Tess. I've got 5 different arrangements right here, and we'll go through and look at the symmetry positions on each one. And if I remember correctly, I had another tiling somewhere, and yeah, now I remember. It'll not be a good example to show right now. But let's focus in on this one for right now. So this is day 1 of Advent of Tess, and I've got 3, so this is a triangle tiling. So I've got closed triangles everywhere. And if I wanted to repeat this further out, I would need to identify my 3 positions of threefold rotational symmetry. And it's not in the twists themselves in this one. Right in the center, I have a position of threefold rotational symmetry. You can see there's these three big, like, ball-like loops coming out. So I'm not in a six-fold position. So I've got a threefold position dead center. I've got another threefold position in the center of this structure that I pointed out earlier. And my third threefold rotationally symmetric position is in the center of this little triangle hole. So I've got these three positions, and just like there was rules with the hexagon and with the square, with the triangle, these three threefold positions make an equilateral triangle. So that's an important thing to know. So then, in this particular tessellation, the only one of these three threefold rotationally symmetric positions that I actually have on a grid intersection is the one that I chose to put in the center. And that's another thing about tessellations. If you're choosing what to put in the center, for me, I always put the position of highest symmetry in the center. With these tessellations, there's three equal positions of highest symmetry. So I choose either the one that looks most like a hexagon or the one that's on a grid intersection. Very practical decisions. And so when I'm repeating this, I know that this point, and this point need to have three exact copies of the same thing around them. And that's what I use to decide what to put where. In the next tessellation, actually, today's tessellation, we have a hexagon in the center. That's a position of six-fold rotational symmetry. Then we've got triangles out here that are serving as positions of threefold rotational symmetry. And exactly between the two threes, there is a 2 sitting right in between two threes and in between two sixes. So that's how I'm seeing the symmetry on this tessellation. Now, tomorrow's tessellation doesn't quite follow that rule. So we have the 6 in the middle. We have 6 equal things going out around it. But those 6 things are different than the hexagon in the middle. And so the most they can be is threefold rotationally symmetric. So we end up with positions of threefold rotational symmetry out here and twofold directly in between. So we've got a 2 in there. So this is an expansion of the symmetry. And just because we're in a tiling with hexagons and triangles, where each hexagon has 6 triangle neighbors and each triangle has 3 hexagon neighbors, does not mean that the triangles are in the positions of threefold rotational symmetry. So that's how I would complete this tessellation, how I would assess the symmetry of this tessellation, shrinking violet. Next up, we've got rhombi here on the outside. And so these triangles are going to, and let me double check that, yes, this is the one that is marked up, not the one that's my demo piece. The rhombi the triangles are going to three different things. They're going to the hexagon, the fat edge of the rhombus, and the sharp edge of the rhombus. And so those triangles have no rotational symmetry in the broader pattern. Okay, so we've got the 6 in the middle. That one's clear enough. But what do we do with everything else? Well, before I said that the maximum symmetry that could go out here is 3. The rhombus doesn't even meet that. So one thing about twists is they've got their maximum inherent symmetry, and then they can also fill positions that are factors of that maximum symmetry. The rhombus has a maximum symmetry of 2, just like we saw with the parallelograms earlier. And so that's going to be a 2-fold position. The 3 is out here somewhere, like here-ish. And then the 2 will lead over to another 6 out here. And now, last but not least, I'm going to grab a copy with the same symmetry as this one, but a different one that I actually have marked up that I don't need to keep unmarked. And so we've got the hexagon in the middle, that's a 6. And this is a different arrangement. The hexagon feeds into the rhombi, not into the triangle. And so we have the densest symmetry option available being the hexagon feeds into the rhombi. The rhombi could be 2s, and the triangles could be 3s. And we can see that whole hexagon complete, and the 2s are exactly in between the 3s. But this isn't the only way. This isn't the only way to repeat this. We could also, instead of doing this, stick the 2 out here and have the 3 even further out. So we could do the 2 right here, we could do it right here, we could just send it on out this pleat as far as we want. And that's what I'm going to be talking about in 2 weeks. By the way, next week you can tune in to see how this continues out. I'm going to be using a different piece to show it, though. I'm going to use this one because it's much more grid efficient than this one. And so we'll be working on how do you continue these out to make bigger tessellations. And you might have guessed by now there's more options than just this, but that requires additional twists to be added and figured out. So we'll stick with the choices that have been made already. And then I will show a expansion of this one with an optionality of how far apart to put repeats of this cluster. So there's all kinds of ways that we can repeat these tessellations, and the symmetries are really going to be our guide for moving forward. So with that, happy folding, everyone. I hope you have a great time, and please do check out Advent of Tess if you're not already doing it. It's really, I've been hearing from people that even if you haven't folded tessellations before, this is the way to get started. So happy folding, and I will see you all next week, where we will explore how to continue folding with the hexagon, triangle, rhombus, triangle tiling. See you then.